Welcome back to Physics 191. I'm Gerard Blanchard. Last time, I introduced the concept of oscillation and all of the equations that are involved with oscillations. This time, we will answer questions about oscillations. Remember that situations with oscillation comprise situations that deal with energy, equilibrium, non-equilibrium. It'll be up to you to determine what equations, what general equations, meaning Newton's first law, Newton's second law, or energy, apply to a particular part of an energy situation. So, let me give you a question so that you can practice this. The period of oscillation of an object in an ideal spring mass system is 0.5 seconds. You pull the mass 5 centimeters from the equilibrium point and release it. What is the speed at the equilibrium point? I'll give you a hint. 5 centimeters is going to be the amplitude of the oscillation. The mass was at rest at its equilibrium point, and then you pulled it 5 centimeters, which means that the mass is going to bounce back and forth 5 centimeters from the equilibrium point. So 5 centimeters is going to be your amplitude. Now, draw a diagram, list your knowns and unknowns, think about the equations that are available to you. You're given the period, so think about the equation for the period, and see what you can do about answering this question. I'll give you some time to try it. Okay, I'm drawing the mass hanging from a spring, and this will be the equilibrium length of the spring, the point at which it would be at rest, and then we pull it down an additional L equilibrium plus 0.05 meters, and then let it go, and that tells us that the object will oscillate back and forth, up and down. It'll oscillate 5 centimeters down and 5 centimeters up, and so we know that the amplitude of the oscillation is 0.05 meters. We're also told that the period of the oscillation is equal to 0.5 seconds. And that is everything that we can get out of the statement of the question. And now, there's a couple ways we can go about answering this question. And that's something that you should realize as well, is that there are different ways about answering all of these questions. One is to consider energy. Energy is equal to 1/2 mv squared plus 1/2 k times L minus L equilibrium squared. Energy is 1/2 k times the amplitude squared, 1/2 mv squared plus 1/2 k times L minus LE squared. And we were asked, what is the speed of the object at the equilibrium point? Well, when L is equal to LE, then this term is equal to 0. And we have 1/2 k a squared is equal to 1/2 mv squared when L is equal to LE, the equilibrium length can divide through by 1/2, and we see that v, I'm going to divide both sides by m and take the square root, and I have square root of k over m times the square root of a squared, which is a, is equal to v. So the speed at the equilibrium point is equal to the square root of the spring constant divided by the mass, square root of k over m, times the amplitude. But we don't know k over m. We do know the period. And we do know that the period is equal to 2 pi times the square root of m over k. The period is 2 pi times the square root of m over k. We know that the period is 0.5. And if we divide that by 2 pi, we divide everything by 2 pi, then that's equal to the square root of m over k. And we can take the reciprocal of both sides, and we would have 2 pi over 0.5 is equal to the square root of k over m. And so now we do know what k over m is. We don't know the mass and we don't know the spring constant, but we do know what the square root of k over m is. So square root of k over m is 2 pi divided by 0.5 times the amplitude of 0.05, and that's equal to the speed at the equilibrium point. And so that is equal to 2 times pi divided by 0.5 times 0.05, which is the amplitude, and we get a speed of 0.628 meters per second is equal to the speed at the equilibrium point. That's the answer we were asked to find. There's another way that we could find that, and that is to realize that since the energy is a constant, the maximum speed will occur at the equilibrium point. In other words, this fixed amount of energy can either be in kinetic energy or potential energy, and the potential energy will be its smallest, which is 0, when L is equal to the equilibrium length. So when the mass is back to its equilibrium position, V is equal to its biggest value. And we know from our kinematic equations that V is equal to, V max is equal to 2 pi times the amplitude divided by the period. And so V max is 2 pi times the amplitude of 0.05 divided by the period of 0.5 seconds, or V max is equal to, well, I've already calculated that. 2 pi times 0.05 over 0.5 is 0.628 meters per second. So asking what the speed of the mass is at the equilibrium point is the same as asking what is the greatest speed of the object. So that's one example of answering a question that deals with oscillation. You have to bring together everything that you know so far to answer these questions. Let's look at another question. The oscillation of an object on a spring has a frequency of 25 Hertz and an amplitude of 1 millimeter. What is the magnitude of the maximum acceleration of the object? And I'll give you a hint. The maximum acceleration of the object will occur when the object is at its extreme point, meaning that the spring is most stretched so that the force is greatest. So the maximum acceleration occurs when the force is greatest, and the maximum force occurs when the spring is most stretched, so at its extreme point, at the greatest length. You don't know mass and you don't know spring constant, but this is another case where it's not the mass or the spring constant that's important, but the ratio of the spring constant, which you can figure out from the frequency, because from the frequency you can figure out the period. Okay, think about that, diagram the situation, list your knowns and unknowns, and give it a start. Okay, so once again, we have a mass on a spring, and we're told that the frequency of oscillation is 25 Hertz. We know that frequency is 1 over the period, so we know that period is 1 over the frequency. So the period of oscillation is 1/25 of a second. So the period of oscillation is 0.04 seconds. We're also told that the amplitude of the oscillation is 1 millimeter. So if this is the equilibrium position, then the mass extends another 1 millimeter. LE plus 0.001 meter. Now, at that point, the spring force is equal to, the magnitude of the spring force is equal to K times L minus L0. So, the maximum acceleration will occur where we have the maximum stretch of the spring. So this would be a Newton's second law situation, or a non-equilibrium situation. And we have the acceleration is equal to the total force divided by the mass. Acceleration is equal to K times the stretch in the spring, which would be equal to the amplitude divided by the mass. And so we see that the acceleration depends on K divided by M times the amplitude. We don't know K and we don't know M, but we can calculate the ratio of K over M from the period, because we know that the period is equal to 2 pi times the square root of mass over K, and that's equal to 0.04. So I will square both sides. 2 pi squared times mass divided by K is equal to 0.04 squared. I will divide both sides by 2 pi squared and then take the reciprocal of that to get K divided by M is equal to 2 pi squared divided by 0.04 squared. And that tells us what k divided by m is. And that tells us that our maximum acceleration is equal to 2 pi squared divided by 0.04 squared times the amplitude of 0.001 meters. And so that tells us that our maximum acceleration of the object is equal to 2 times pi in quantity squared divided by 0.04 squared times 0.001. And that gives us a maximum acceleration of 24.7 meters per second squared. So the important thing to realize in this question is that the maximum acceleration occurs when you have the maximum force, which means that the spring is stretched to its maximum, or in other words, L minus L0 is equal to the amplitude. The other thing to realize is that when you're given the period, you know the ratio of spring constant to mass. You don't necessarily know either one of them separately, but often you don't have to. Often it is the ratio of spring constant to mass that matters. Let's look at another question. A baby jumper consists of a cloth seat suspended by an elastic cord from the lintel of an open doorway. The unstretched length of the cord is 1.2 meters, and the cord stretches by 0.2 meters when a baby of mass 6.8 kilograms is placed into the seat. The mother then pulls the seat down by 8 centimeters and releases it. What is the period of the motion? What is the maximum acceleration of the baby? And what is the maximum speed of the baby? Now, this situation is actually two different situations. The first is you have the unstretched cord, then you put the baby in the seat, and that stretches the cord, and we have equilibrium. So that will let you calculate the spring constant of the spring. The next thing to do is to pull the baby down, and then we can calculate the force on the baby. And then finally, we can calculate the speed of the baby. So go ahead and get that set up. Draw your diagram, list your knowns and unknowns, and then I will guide you through that. Okay, I'll draw a few diagrams here. Here is the baby seat. I guess it looks something like that. And the unstretched length is 1.2 meters. Then the next thing we do is we put the baby in. Put the baby in the jumper, and that stretches the cord to L is equal to 1.4 meters, because the cord stretched by 2.0 meters when the baby of mass 6.8 kilograms, or weight is equal to 6.8 times 9.8 newtons per kilogram, is offset by the spring force K times L minus L0. So the first situation that we have here is an equilibrium situation where the cord is supporting the weight of the baby. And so we have equilibrium and we have force total is equal to 0. Force total in the y direction is equal to 0. So that says that K times L minus L0 must be equal to the weight of 6.8 times 9.8, or this minus that equals 0, which is the same thing. And L minus L0 would be 1.4 minus 1.2 is equal to 6.8 times 9.8. That gives us a K of 6.8 times 9.8 divided by 1.4 minus 1.2, and that gives us a spring constant of 6.8 times 9.8 divided by 1.4 minus 1.2 gives us a spring constant of 333 newtons per meter. So the spring constant of the elastic cord is 333 newtons per meter. Now, the mother pulls the seat down again and releases it. She pulls the seat down by 8 centimeters and releases it. So this becomes our new equilibrium position. And she pulls it down another, with the baby in it, L is equal to LE plus 0.08 meters. And what that tells us is that when the baby bounces, he will bounce with an amplitude of 8 centimeters, 0.08 meters. What is the period of the motion? What is the period of the oscillation? Well, period is equal to 2 pi times the square root of mass over K. So the period would be 2 pi times the square root of the baby's mass, which is 6.8, divided by K of 333. So the period of the oscillation is 2 times pi times the square root of 6.8 divided by 333. And that would be 8.98 seconds. So we've answered the first question, which is, what is the period of the oscillation? And that would be 8.98 seconds. The second question is, what is the maximum acceleration of the baby? Well, the maximum acceleration of the baby occurs when the baby is first let go, or any time that the elastic cord is at its maximum stretch. And that would be 8 centimeters beyond the equilibrium length. So we have a non-equilibrium situation, and the acceleration is equal to the total force divided by the mass, or the acceleration is equal to k times the amplitude divided by the mass, or the acceleration is equal to 333 newtons per meter times the amplitude of 0.08 meters divided by the baby's mass of 6.8 kilograms. That tells us that the baby's acceleration, maximum acceleration, is going to be 333 times 0.08 divided by 6.8, and that would be 3.9 meters per second squared. And that was the second question that we were asked to find. And the third question is simply, what is the maximum speed of the baby? Well, for that, we can go to our kinematic equations and get V max is equal to 2 pi times the amplitude over the period. So V max is equal to 2 pi times 0.08 meters divided by the period. I'm sorry, hold on one second here. I'm going to double check something. 2 times pi times the square root of 6.8 divided by 333. Yes, I'm sorry. I made a mistake here. This shouldn't be 8.98. This should be 0.898 seconds for the period. So the period of the oscillation is 0.898. I think I said that, but I wrote it down wrong. So the period is 0.898 seconds. So it gives us Vmax of 2 times pi times 0.08 divided by 0.898 seconds, and that gives the baby a maximum speed of 0.560 meters per second. And that was the third question that we were asked. What is Vmax? What is the acceleration? What is the period? The period, 0.898 seconds. Acceleration, maximum of 3.9 meters per second squared. And Vmax of 0.56 meters per second. And that's everything that we were asked. Those are some examples of questions dealing with the oscillation of a mass on a spring. Now, masses and springs aren't the only systems that demonstrate oscillations. Another system that demonstrates oscillations is a pendulum, consisting simply of a mass on a string. So to wrap up with Chapter 10, I'm going to talk a little bit about pendula. A pendulum also exhibits simple harmonic motion, and the period of the pendulum's motion is equal to 2 pi times the square root of the length of the pendulum divided by g, the gravitational field strength. So T period is equal to 2 pi times the square root of the length of the pendulum divided by gravitational field. You'll notice that mass doesn't appear in this equation at all. So the period of a pendulum depends only on the length of the pendulum and on the gravitational field. And this is very fortunate because we can measure length relatively easily. It's one of the easier things for us to measure. And this gives us the possibility of measuring time using a pendulum. Think about a pendulum clock. We can measure time using a pendulum if we know G, or conversely, if we have a timepiece, if we have a way of measuring time, we can use this to measure the gravitational field strength. So this was one of the first tools used for measuring gravity. So let me demonstrate that for you. Here we have a pendulum. There's a thread hanging down here and a mass hanging from it. The length, let me calculate that, or let me measure that. The length is 39 centimeters. Let me check again. Yeah, actually it's more like 38.5 centimeters. So the length, we'll make a table here. The length of the pendulum is 0.3. What did I say? 0. Actually, I'm going to go with 39 centimeters. 0.39 meters. 0.39 meters. And I'll make a note that this is our 50-gram mass. So mass in kilograms is 0.05. And I will measure the time in seconds. Actually, what I'll do is, as I did last time, I'll measure the time for 10 oscillations, and then I'll just divide by 10. So I'm actually going to write down the period this time. Okay, so remember that an oscillation is a swing back and forth. So one oscillation is one back and forth. So I'm going to measure the time for 10 back and forths. Okay, and here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was 12.63 seconds. So the period of the oscillation was 1.263 seconds. Now the next thing I'll do is I will change the mass out. And here we have our 100-gram mass, or 0.1 kilogram mass. And the length of the pendulum is still the same. So length is 0.39. The mass is now 0.10. And our theory tells us that the period of oscillation will be the same, or at least close enough. And here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I get 12.78 seconds, which would be 1.278. So very close, very close. Close enough to the ability, close enough given my ability to actually measure these times using my eye and a stopwatch. So what we've seen there is that the period of the pendulum doesn't depend on the mass that's hanging from it, which, as I said, is fortunate because mass turns out to be one of the more difficult things for us to measure. Length is relatively easy, time is a little bit harder, and mass is more difficult. Let us change the length of the pendulum and see how that changes the period. If I shorten the pendulum, make it shorter, okay, we would expect a shorter period. Okay, so let's just see. Yes, I think that's oscillating faster, but we can measure it as well. So now we have to know our length. What is our new length? Our new length of our pendulum is 19 centimeters. Whoa, 19 centimeters, or 0.19 meters. And this is our 10 kilogram mass, not 10, our 0.1 kilogram mass, or a 100 gram mass. And let's see, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was 8.75 seconds for 10 oscillations, or 0.875 seconds for 1 oscillation. Let's swap out our masses again, just to make sure that we get the same time. Okay, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I get 8.65 seconds. So for 0.19 meters, 0.05 kilograms, I get 0.865 seconds. So we'll lengthen the pendulum again. There we go. Okay, and how long is that? And that is 70.5 centimeters, or 0.705. Our mass is 0.05 kilograms. And let's find out what our period is. So at the very least, we can predict that it'll be longer than 1.2 seconds, which is what we had for 39 centimeters of length. Okay, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I get 16.94, which would give me a period of 1.694 seconds. And we will take a final bit of data. We'll swap out for the other mass. 0.705, 0.10 kilograms, and there we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I get 1.684. So, once again, very close within my ability to measure. So, if we take a look at our data now, we see that we have 2 measurements at each length. We have a length of 0.39, 0.19, and 0.705 meters. with two different masses, and at each length the times were close enough. 1.2 and 1.26, 1.27, 0.875, 0.865, 1.69, 1.68. So what we can see from there is that the mass didn't make a difference, as we expected. Now that we have an experimental value for our time, let's calculate the theoretical value for the period. And the theoretical value, according to our equation, is that the period is 2 pi times the square root of L over G of 9.8. Okay, here we have 2 pi times the square root of 0.39 divided by 9.8, and that is equal to 2 times pi times 0.39 times the square root of 0.39 divided by 9.8, and I get 1.25. So once again, very close, 1.25 seconds. So this is measured in seconds, 1.25. So that equation worked out very well for our 0.39 distance. How about 0.19? We have 2 pi times the square root of 0.19 divided by 9.8 equals 2 times pi times the square root of 0.19 divided by 9.8, and that is 0.875. 0.875, which is once again very close. That's exactly the same as what we got for the larger mass and very close to what we got for the smaller mass. And finally, 2 pi times the square root of 0.705 divided by 9.8 equals 2 times pi times the square root of 0.705 divided by 9.8 gives us a period of 1.69 seconds. 1.69. So very, very precise. In fact, a lot more precise than we got for our masses on a spring. If you remember last time, there was a lot of experimental error in those calculations. So the pendulum is a very useful tool for measuring time precisely or for measuring G precisely if you have another way of measuring time. So throughout history, the pendulum has been a very useful tool. So that wraps up our chapter on oscillations, chapter 10. Next time, we will revisit gravity. We have been specifying all along that we were dealing with gravity close to the surface of the Earth, where gravity was a constant 9.8 newtons per kilogram. Now what we're going to do is we're going to explore Newton's universal theory of gravity, which will help us deal with situations when we're not at the surface of the Earth. And that is a topic all unto itself. We'll come back to that next time. And until then, think physics.